Hi, David Pecker here. In this video, we will discuss how rocket engines work. We will start out by reviewing Newton's 3 laws of motion. Then we will discuss how reaction engines work. And finally, we will discuss what ultimately limits rocket engine performance. Throughout this video, we will be using Newton's 3 laws of motion, so we begin by reviewing them. The first law states that objects at rest stay at rest, and objects in motion continue moving at a constant velocity unless acted upon by a net unbalanced outside force. The second law is force equals mass times acceleration, and the final law states that if object 1 exerts a force F12 onto object 2, then object 2 exerts a force F21, which is equal to minus F12 on object 1. Having reminded ourselves of Newton's laws of motion, let's go ahead and start our discussion of how rocket engines work. And to do so, let's go ahead and draw a rocket. Here I start out by drawing the rocket engine, and then the fuel and the oxidizer tanks. Now, the goal of every rocket is of course to carry some sort of payload, so let me go ahead and draw the payload at the tip of the rocket. Next, I draw the aerodynamical shell of the rocket, which ensures that air flows around the rocket smoothly. Finally, I'm going to draw the two turbo pumps and the lines which carry fuel and oxidizer from their tanks to the rocket engine at the back of the rocket. Now, what sort of fuels can go into the fuel tank? There are lots of different kinds of rocket fuels, and here we focus on the liquid-fueled rockets in particular. For its main engines, the Space Shuttle used to use liquid hydrogen. RP-1, or Rocket Propellant 1, which is basically refined kerosene, is another popular rocket fuel. It is used by many Soviet rockets like the Soyuz, and also by SpaceX Falcon 9 rocket. Currently, there is a lot of excitement about using liquid methane or liquid CH4 for a rocket fuel, and indeed, this is a fuel of choice for both SpaceX Starship and Blue Origin's New Glenn rockets. There are many other types of rocket fuels, but the main goal of a rocket fuel is to be stuff that burns really well. And when I say it burns really well, it must burn really hot and give off lots of energy. Rockets need to carry their own oxidizer, and the standard choice is just liquid oxygen. Why do rockets need oxidizer? Well, in order to have combustion, we need both fuel and oxygen, and the oxidizer is a component that provides the oxygen. And since there is no oxygen in space, the rocket needs to bring its own. Now, how does a rocket engine make thrust? That is, how does it produce force which pushes the rocket forward? To understand this, we need to see what happens inside the rocket engine. A rocket engine is basically composed of two parts: a combustion chamber and a nozzle. Now, what is the job of the combustion chamber? The turbo pumps feed fuel and oxidizer inside the combustion chamber, and that is where the burning happens. That is where fuel and oxygen combine. What is a typical chemical reaction that is happening inside the combustion chamber? Well, let's focus on the case of a methane engine. Inside the combustion chamber, methane is combined with oxygen to produce carbon dioxide, water, and lots of heat. This is exactly the chemical reaction that happens in the SpaceX Raptor engine, which will power the next generation space rocket that SpaceX is making, the SpaceX Starship. The Starship is currently undergoing development, and SpaceX has provided some pretty cool video of their test flights. Here is one showing a prototype hopping up to an altitude of 150 meters and then landing again. Now, a question that often comes up with students is how do rockets steer themselves? Well, they steer themselves by pointing the rocket engine in different directions. And here you can see the rocket engine at the bottom of the Starship swiveling in order to controllably bring the Starship to a landing.
Full duration.
Another popular combination is to use hydrogen and oxygen, both in liquid forms. And the product of this combustion is simply water and heat. And this is exactly the chemical reaction that was used by the Space Shuttle main engine. Here we are, looking at the three main engines of the Space Shuttle Atlantis, and the white hot flames coming out of them is actually nothing but superheated water. The large orange flames, on the other hand, are produced by the solid rocket boosters, which use aluminum perchlorate as the oxidizer and aluminum powder, iron oxide, P-ban, and epoxy as the fuel. Now that we have a pretty good idea about the role of the combustion chamber, what does the nozzle of the rocket engine do? Well, it converts the heat energy of combustion products into linear motion of these combustion products. So here again is our schematic image of the rocket engine, showing the nozzle to the left and the combustion chamber to the right. Inside the combustion chamber, the combustion products are at very high temperature, but they're pretty much thermal, which means they move in every which way. In order to take this thermal energy and convert it into a thrust, we must make the combustion products move essentially all in the same direction out the back of the engine. Reorganizing the flow of the combustion products is the job of the rocket engine nozzle. Now, we saw in the videos of the various rocket engines that rocket engines indeed throw the combustion products straight back at high velocity. But why do they do that? The rocket engine, and specifically the nozzle part of the rocket engine, exerts a force on the combustion products that accelerates these combustion products in the aft direction of the rocket. From Newton's third law, we know that forces come in pairs. Now, what's the third law pair here? Well, as the rocket engine exerts a force on the exhaust gases exert a force back on the rocket engine. And this is exactly the force that pushes the rocket engine forwards. This thrust force is exactly what accelerates the rocket forward. To summarize, the rocket engine applies a force to the combustion products, which accelerates the combustion products in the aft direction. By Newton's third law, there is a force on the rocket engine, which is in the opposite direction, and which pushes the rocket forward. Now let's illustrate this point by considering the following thought experiment. Suppose I have a chair on wheels, a really rolly chair, and inside this chair I'm going to place an experimentalist. Next, I'm going to give a dumbbell for the experimentalist to hold. I'm going to set up this experiment so initially the chair, the experimentalist, and the dumbbell are all at rest. Next, I'm going to instruct the experimentalist to take the dumbbell and throw it as hard as the experimentalist can to the left. What do you think is going to happen in this situation? Do take a moment to think about this. In order to make the dumbbell fly, the experimentalist must apply a force to the dumbbell, which we will call Fe applied to D. This is exactly the force which accelerates the dumbbell to the left and makes it fly. By Newton's third law, the dumbbell applies a force to the experimentalist, which we will call Fd to E, and this force makes the experimentalist move in the opposite direction. To summarize, the dumbbell flies to the left and the experimentalist rolls to the right. If you've guessed this outcome, then go ahead and pat yourself on the back, because you have the correct intuition for understanding how rocket engines work. Because in the old textbooks, Newton's third law was defined in terms of action and reaction, it is typical to label the mass that we throw away, in this case the dumbbell, as the reaction mass. And therefore rocket engines and also experimentalists with dumbbells are called reaction mass engines. Now a question which comes up over and over again is, do rocket engines work in vacuum where there is no atmosphere and hence no air to push against? Let's go ahead and take a collective moment to think about this question. So what is the answer? The answer is that rocket engines do not work by pushing against the air. Instead, they work by throwing reaction mass. And you intuitively know that this is the right answer by appealing to the example of the experimentalist in the rolling chair. If we take the chair to the moon, where there is no air, put the experimentalist in a spacesuit, and let the experimentalist throw the dumbbell, the experimentalist should roll back, just like on Earth. Indeed, it turns out that rocket engines work slightly better in vacuum than in the atmosphere, and that is because in vacuum there is no atmospheric pressure to inhibit the throwing back of the combustion products. A more complete answer is that rocket engines work quite differently from airplane engines. As we have already mentioned, rocket engines work by taking reaction mass and throwing it back, and in turn getting a force applied to the engine, pushing it forward, called the thrust force. Now let's consider what happens in propeller aircraft engines. That is, airplane engines that have a spinny thing, like this A400 military transporter built by Airbus. Well, the airplane engine spins the propeller round and round, and the propeller pushes on the air. By Newton's third law, the air pushes back on the propeller and hence applies a thrust force to the airplane. Unlike the rocket engine, the propeller aircraft engine would not work in the absence of the atmosphere, as it would have nothing to push against. Now what about jet airplane engines? That is, engines that look more like this. It turns out that most modern jet engines have pretty big fans, which push on the air just like propeller engines. Here is a cutaway drawing of the GE9X engine from GE Aviation website, showing the cutaway of the engine that powers the Boeing 777. As we have already mentioned, most of the thrust produced by this engine is provided by the giant fan at the front of the engine. Now, the area highlighted in blue is the power core of the engine, and this part produces the power to power the fan. The turbines at the front of the power core compress the incoming air. Fuel is injected into the combustion chamber and is burned together with the incoming air. And then the power generation turbines extract the heat energy from the combustion products and use that to power the big fan at the front of the engine. A small fraction of the heat energy of the combustion products actually escapes the engine and produces a little bit of residual reaction mass, thrust, just like a rocket engine. Unlike rockets, airplanes do not carry oxidizer on board, so in vacuum, even this residual reaction mass thrust would not be generated, as there would be no air to burn inside the engine. Now, what are the basic limits on rocket engine performance? Now, rocket engines burn chemical fuels. The rocket engines themselves are also made from chemicals, typically metal alloys. Now, why do I bring all this up? Well, both of these are united by the chemical bond. The strength of the chemical bond is really the ultimate and fundamental limit on a rocket engine performance. The strength of the chemical bond first limits how much energy we can generate by burning the fuel. that is how much energy per kilogram of fuel is available. This is really a fundamental limit. While different fuels can have a little bit more or a little bit less energy, the strength of the chemical bond sets the ultimate limit on how much energy can be inside the rocket fuel. Second, the strength of the chemical bond limits the melting temperature of the rocket engine. Now, a melting rocket engine does us no good, and therefore the combustion products inside the rocket engine better not exceed the melting temperature of the rocket engine itself. The chemical energy stored in the rocket fuel gets converted into heat energy inside the combustion chamber. Next, inside the nozzle, the heat energy is converted into the kinetic energy of the rocket exhaust. E-chem is the chemical energy that is released by the combustion process per exhaust gas molecule. Now, E-chem gets converted into E-kinetic, the kinetic energy, which is equal to 1/2 mv squared, where m is the mass of the exhaust gas molecule, and v is its velocity at the nozzle exit. The kinetic energy cannot exceed the chemical energy, as of course all engines, including rocket engines, suffer from some losses. And therefore the chemical energy sets the ultimate velocity of the exhaust gas, and that in turn sets the ultimate performance of the rocket engine. While this notion that the higher the exhaust gas velocity, the better the performance of the rocket engine makes intuitive sense, when we discuss the rocket equation, we will indeed see the theoretical basis for this statement. We have now covered the basic concepts underlying the functionality of rocket engines. Thank you for watching the video, and remember to stay curious.